Hello, welcome to the second lesson of sectoral structures theory. Today we will show a very important, or we will introduce a very important concept in this theory, and we will find our first useful result using this concept. So we will introduce the concept of alpha joints, which are very fundamental in this theory. If we have two congruent sectors that are attached such that they share one edge or one radius, and such that the arc of the two sectors or the arcs of the two sectors are continuous. So basically we have two congruent sectors that are attached in this manner. We will refer to those as continuous sectors. And we will refer to this point here where they attach, where their arcs intersect, as an alpha joint. This is very fundamental in this theory. So this will be the alpha joint. And to indicate that sector V and sector U are continuous, meaning they are congruent and they share an alpha joint, we will use this wedge symbol, which we have borrowed from algebraic geometry, geometric algebra. We will say V wedge U. Of course, here it simply indicates that they are continuous sectors. So V wedge U. Now, if we have multiple continuous sectors, like here, we have A, B, C, D, we will simply say A wedge B, wedge C, wedge D. For now. Later on, we will use simpler ways to express them. Now, if we have X number of continuous sectors, of course, they will have X minus 1 alpha joints connecting them. Now, we will refer to a single we will refer to the curve that is formed by joining all these arcs of the sectors as the sectoral curve. So this arc right there that is formed, we will call it the sectoral curve, and we will talk a lot more about it in the future. We will refer to any group, any individual group of continuous sectors as a part. So we will later see that sectoral structures can be made of multiple parts. Each part is really a group of continuous sectors. And we will call the number of sectors in a given part as the weight of that part. So you'll see this language is somewhat similar to some aspects of number theory, and we will see that it's really helpful in the future. So this is a part, and the weight of this part is 4 because it has 4 sectors in it. Now, if you remember, we talked earlier about the central angle of a sector, and we said it's basically equal to 2 pi divided by n, where n is the total number of congruent sectors. Remember, here we're talking about congruent sectors within a circle. Now let's take, for example, this sector here. This sector is one of 8 sectors, 8 congruent sectors. So for this reason, we will say that the degree of this sector is 8. Not to confuse it with the measure of the angle. And for this reason, we're going to try to avoid talking about the central angle and the degree of the angle. We will rather focus on the arc length or the sectoral or the length of the sectoral curve. So we will really focus our language on the curve when we're talking about the measure of the angle. And whenever we're talking about the number of congruent sectors, we will use the word degree. And again, this will have some applications later on. So n will refer to the degree of the sector. Now, let's look at our first application of our alpha joints. If we have a circle divided into n congruent sectors, how many groups or how many groups of continuous sectors can we form within this circle? So of course you can't form it with one sector, it has to be at least two. So you can form it with this one and that one, with that one and that one, and so on. You can also form it with three continuous sectors. So it'll be this one, and then these, and so on. You can form it with four until you reach n, which is the total number of sectors. So in order to find out, our first combinatoric challenge here is how many groups of continuous sectors can we form for within a circle that is divided into n congruent sectors. We will say pi will be, p is going to be part. So pi, which belongs to circle n, where n is the number of or the degree of the sectors, such that it's gonna be between two continuous sectors and n. So the weight of each group, or the weight of each part, the weight of each part must be between 2 and n, including 2 and n. We will say that P is going to be from the sigma from I equals 2 to n, such that of Pi, such that it equals to n minus 2 times n plus 1, where 1 indicates the situation where you include all the sectors, so where the whole circle is included. Now this gives us, of course, n squared minus 2n, and then we add 1 to it. And then this can be simplified into n minus 1 squared. So the answer is simply n minus 1 squared. So basically, if we have a circle divided into n congruent parts, then the number of continuous sectors that can be formed is equal to n minus 1 squared. So for this example, we have 8 sectors. N minus 1 is 7, 7 squared is 49. So we have 49 possible combinations of continuous sectors. Now what's even more interesting is the following. We remember that n is equal to 2 pi over theta. So we're going to use that. We're going to say p is equal to 2 pi over theta minus 1 squared. We're going to rearrange this a little bit into 2 pi minus theta divided by theta squared. So now I wanted to focus on a single sector. This is theta. And then if we say 2 pi minus theta, that's the external angle. And we're going to call this delta. We know that delta is 2 pi minus theta. So we see that here. So we substitute delta, and then we can say that P is equal to delta over theta squared. So this is our first very interesting finding. So in order to find the total number of combinations of continuous sectors, what we have to do is we divide the central angle divided by the we divide the external angle over the central angle, and we square it. So that's our first very interesting connection between the angle and our combination or our combinatoric problem. Thank you.